In addition to central tendency, every variable can be characterized by its variation in shape. In terms of variation, that is how spread out is your data. And the formula that we will use is variance and standard deviation. And we'll have formulas for population as well as sample. Another way to look at the variation is a simple measure that's called range, and that's just the largest value minus the smallest value. It does not take into account how the values are distributed. You don't know if they're clustered in the middle, evenly distributed, clustered near one or both extremes. Using the range as a measure of variation when at least one value is an extreme value is misleading. An extreme value is called an outlier. So the formula for variance, population variance, is the summation from I equal 1 to capital N, x sub I minus the mean squared divided by n, capital N. The variance for sample will be the summation I equal 1 to lowercase n, x sub I minus x bar squared over or divided by lowercase n minus 1. We have found that if you divide the sample by lowercase n, it does not emulate the population variance, so make sure you divide by n minus 1. And I'll let you think about, if you don't divide by n minus 1, does it overestimate or underestimate it? Now next, talk about standard deviation. Standard deviation for population, you just take the square root of the variance, and the same thing for sample. Just take the square root of the variance. So if I want to find the variance and standard deviation for the sample data, you have to know if our data is sample or population. For this set of numbers, 1, 2, 3, 4, 5. So n is 5, and we know we have to know the mean. So x bar will be 1 plus 2 plus 3 plus 4 plus 5 divided by 5, and that's going to be 5. That's going to be 3. So x bar equals 3. Now, okay, sample. So we're finding s squared, and this is the variance we're finding. So we'll take our first data point, which is 1. We subtract the mean, which is 3, and we square it. And then we go to the next one. I becomes 2 now. So I take my second data point, which is 2, minus the mean squared, plus the next data point minus the mean squared, plus the next data point, which is 4 minus the mean squared, plus the last data point, which is 5 minus 3 squared, and I divide by 5 minus 1. So that's going to be a negative 2 squared plus a negative 1 squared plus a 0 squared plus a 1 squared plus 2 squared divided by 5 minus 1, which is 4. So if you square those, 4 plus 1 plus 1 plus 4, all over 4, you end up getting 2.5. So the standard deviation, which is S, would be the square root of 2.5, and that gives me approximately 1.5811. Now, I've given you sample data here. I've got set 1 and set 2, and I want you to look at set 1. And then I want you to look at set 2 and tell me which set of data or numbers is more spread out. which would have a greater variance? And I believe all you guys would say set 1 has greater variance. It's more spread out. And I actually calculated the standard deviation for each one. And the standard deviation for set 1 was 3.16. And for set 2, it was 1.13. So this had a greater variation. And normally when I look at how spread out my data is, I will use the standard deviation calculation because it's linear, it's in linear units, and that's how my mind works. So I'll usually, both variance and standard deviation tell you how spread out your data is, but variance is in square units, standard deviations in linear units, and that's how my brain works. All right, let's move on. Whenever two samples have the same units of measure, the variance and standard deviation for each can be compared directly. So in this example, we're looking at, let me see. Suppose an automobile dealer wanted to compare the standard deviation of miles for trading cars for a specific year. Standard deviation for Buicks was 422. Standard deviation for Cadillacs was 350. So we're talking about the standard deviation of each. So we could say that the variation in mileage was greater for the Buicks because 422 is greater than 350. But what if a manager wanted to compare standard deviation of two different variables, such as sales per salesperson and the commissions made by these salespeople? We're going to have to use revert. And what we're going to use here is something called the coefficient of variation. And the coefficient of variation is the standard deviation divided by x bar, or if you happen to be given population, it would be sigma over mu. So what I have here is sales with a mean of 87, standard deviation is 5, commissions 5,225, and standard deviation 773. So my coefficient of variation is 5 divided by 87. And that's about 0.057 or 5.7%. And commissions coefficient of variation. See, what I've done, we were talking about two different things. We're talking about sales and commissions. But with this coefficient of variation, if I convert to the CV, then I can compare those numbers. So this would be 773 over 5,225, and found that to be 0.1479 or 14.79%. So since the CV is larger for commissions, we would say the commissions are more variable. Than the sales. All right, now, last page of notes. This will be fast. Skewness. Let's start here in the middle. For symmetrical data, if you cut it in half, you get the same amount on both sides. That's symmetrical. And that means your mean would equal the median. Now go back to the top. This is left skewed. It's pulled out more in the left tail. In this case, when it's left skewed, your mean is less than your median. The bottom one, right skewed, it's positively skewed. It's pulled out in the right tail. And here, the mean would be greater than the mean. You will graph data and you'll look to see if it's symmetrical, left or right skewed. So you need to know how to tell the difference between these three.